One of Albert Einstein's postulates is that nothing can move faster in space than light. This postulate must have caused the greatest uproar in the scientific community of the time, for the assertion clashes at first with the instant form with which our vision spans the entire celestial vault in a dark cloudless night. Our satellite dishes and telescopes, like Hubble, can also track the cosmic radiation very close to the Big Bang, and do so instantly. If the light does not shift instantly into space, how is that possible? Among the many hypotheses raised, what stands out most is that the light emitted in the Big Bang and the expanding galaxies would be formed by continuous electromagnetic waves. Imagine a ball of wool, in which one of its points was placed next to the Big Bang event, and the continuous thread of light was rolled from there until it reached us on Earth today. So it would be justifiable to imagine that it does not matter if the light is followed in one direction or the other. That is, the Big Bang would be in our past, because it would have been from there that the light would have gone. This thesis could no longer be sustained after the advent of the photoelectric effect, for it showed that the thread of the wool ball, which would bind us directly to the past, is totally fragmented or punctured. When we introduce a new element into the context, represented by the isolated observer, endowed with a memory, some things begin to make sense. This procedure often bugs those who believe that there's only what can be measured as we move away from the outside, where the galaxies are sighted, and we begin to worry about how our consciousness gives meaning to external events. One cannot think, without causing laughter in disguise, that our brain could be able to create reality. However, it is likely that our brain has been designed to convey reality, in the form of information, into the realms of our consciousness. When it does, it is assumed that this would never happen in real time, because we need comparative patterns and stereotypes that can be revisited at any time, starting to compose our memory. It resides right there, one way of explaining the instantaneous way in which everything can be observed around us. It is hard to admit that our consciousness could be acting intermittently in our day-to-day life, simply because nothing exists outside of it. For we can comment on anything, we depend on the constant presence of information. This would be what makes the thread of the aforementioned ball uninterrupted. That same thread that would link us directly to our own past. It's our memory that would be supporting the concept of virtually continuous waves. The photoelectric effect is one of the mainstays of quantum mechanics, and, basically, tells us that any form of measurable energy is quantized or packaged. In addition, the quantization process would be timeless, since when a photon strikes an electron and the quantum spreads, both appear simultaneously, with no measurable interval of time separating them. This prevents us from finding an electron in the interval between two subsequent energy levels of the atom, which creates uncertainty. Since the time of quantization does not exist, or cannot be directly measured, and we need scattered light to see the particle, it becomes irrelevant to know what the distance would have been previously traveled by the photon of light. The tracking principle is the same, whether it is used by a microscopist or an astronomer behind a telescope. In any case, there is still a vague feeling that there was a before and after of the spreading, which cannot be confirmed or denied. So we see that these issues are dependent on the presence of the observer, although the universe does not seem to be very concerned about what we think about it. The cogitations on the 13.7 billion years that would separate us from the Big Bang result from late evaluations, or that would have happened after the spreading of the cosmic radiation. So, it is appropriately called cosmic background radiation. It may be assumed, for example, that cosmic radiation and light from galaxies have always been here, at least from our point of view, without it being relevant to know whether there has been an earlier displacement of light into space. In any case, to be seen by the observer, the light would need to be subjected to a local packaging process. This packaging or quantization would have caused the separation of light in space, with the first assuming the function of being the messenger of the galaxies. The speed of 300,000 kilometers per second, which is attributed to cosmic radiation, would be part of this package, as well as the Doppler effect. The current behavior of the scientific community is reflected in its way of evaluating the distances and speeds of the stars and galaxies they form. It is assumed that light in space would form a whole, one thing only. So, if you follow the light in the direction of the past, you would reach the corresponding point in space, occupied by a star. The problem is that we cannot follow space directly, because it would have separated itself from the light at the exact moment of photon scattering, which would be behind the uncertainty principle at position or velocity of the particles. When space is analyzed through light and cosmic radiation as a whole, it starts to assume the same behavior as an elastic strip, which is what defines the phases of the harmonic motion of the radiation. What would behave like an elastic would be light, not space. This would have spawned a number of mistaken assessments of space, which would now be dependent on its messenger of totally different behavior. When you stretch an elastic, the force points in the opposite direction of stretching. If space and light formed one thing, this would assign a negative energy to the vacuum during the expansion phase of the universe, just as it would in an implosion. the galaxies would tend to slow down. If, on the other hand, you left the elastic free to relax, the force would also point in the opposite direction, resulting in acceleration. It is said that the energy involved in this system is conservative, so the galaxy should accelerate only in the phase of contraction of the universe, which does not occur in the practice of Doppler. We conclude that, because we are subjected to the empire of electromagnetic radiation, there would be a principle of exclusion between the phases of the harmonic motion of light. We would be seeing the galaxies moving away from each other, but out of their own time. Without this, inflation would cease to exist, because, due to the complementary contraction of time, we could not remember the inflationary phase in the present of the universe. An inversion in the direction of the arrow of the time next to the observer would be necessary. An inversion that, even in an apparent way, would point the sense of arrow in the direction of our own past. In fact, it would be the contraction of space in the presence of the acceleration of movement and the dilation of time which would be exposing the previous opposite phase, that of expansion of the universe. By acting like an immense eraser of information, even if they continued there, the expansion, followed by the complementary contraction of time, would have mixed the distinct effects of the two phases of the harmonic motion of light. As the elastic contraction phase would be the only one responsible for direct access to the information after photon scattering, the exclusion between them caused the expansion and contraction of light to become trends, which would have been suspended toward the infinite. Thus, should be justified the Einstein's hypothesis that the universe should even be static. I add that this would only be possible in a place of the universe without memory or where time could not be measured directly.